introduce our panelists here, as we can, which of course now I'm having trouble finding my notes. We'll start off with Representative Dennis Hedke. He is a graduate of Kansas State University with a Bachelor of Science in Geophysics and a graduate also of the University of Virginia School of Engineering with a Master's in Materials Engineering. All right? Did I get that? He is a legislator in the Kansas State House representing the 99th District, which is Andover, East Wichita. He also is a co-owner of the, get this wrong, Hedke Sanger Consulting, which works with a number of industries around the oil and gas industry, as well as doing research for the Kansas Geological Survey. On his left, right? My left. Is Dr. Charles Rice. He is a distinguished professor of soil microbiology. Thank you. My notes disappeared off when I set it down. Microbiology at K-State. He does research around carbon in soil and how that has effect on the climate. And to his right is Dr. Johan Fedema, who is at KU. We'll forgive him for that, since we've got a lot of K-State people around here. His primary interest, he is chair of the Department of Geography at the University of Kansas, and his primary interest is understanding the human impact on the Earth's surface and the consequences of these actions on the environment. Both Dr. Rice and Dr. Fedema serve on the Intergovernmental Panel on Climate Change. Don Tessie, our last panelist, is a fifth-generation Kansas farmer and president of the Kansas Farmers Union. He and his family farm a little over 1,000 acres in Potawatomi County, and he would like to be able to pass that on to his 4, soon-to-be 5, great-grandchildren. So, great-grandchildren, right? Grandchildren. Sorry about that. We're going to start with Representative Hedke and work our way this way. Each of them will have up to 4 minutes. We have a timekeeper here who will tell you when you get to 2, and then 1, and then a half, and then stop. So when we have a little bell that will go off at the stop point. So we'll start, and each of you have a chance to give a presentation, your response to the bill.
Well, thank you, Carol and Lori, for all of your efforts in pulling this together. Sierra Club, co-sponsor, you've always done a wonderful job, and we appreciate that. I thoroughly enjoyed the film. It's the third time I've seen it now. Learn something new every time I see it. I thought the photography was just outstanding, and the National Geographic support was awesome, I'm sure, and the effort put forth by the photographers, the whole team was just incredible. I would just say this, that it would have been, as a scientist, to me it would have been a much more interesting film if they would have had some discussion of the fact that Antarctica sea ice extent is at maximum levels since it's been recorded, and that the ice sheet thickness in Antarctica is also at record thicknesses. So the point I'm making with that is that in a regional sense, which is where the focus of this film was based, Iceland, Greenland, and northern parts of North America and the Arctic region, there are certainly some calving, and Annette and my wife, visited Alaska 2 summers ago and got to witness at the Harbor Glacier some really interesting calving, just thoroughly enjoyed that. But there are glaciers that are advancing, and the small point was made there that some 4 out of whatever the number was are advancing, but the vast majority were declining in their size in the area that they study. But we have a global system, and it's very important to keep that in mind at all times. And I want to believe, I want to present you an image here that I hope will give you some additional perspective. There was this thing that was the medieval warm period back in the 1200s, and it kind of got washed out by some scientific endeavors in a famous film that you saw some years ago called The Truth. That global warming period was minimized, if not extinguished, in that famous hockey stick graph. However, there's a castle in the UK, and it's in my handout back there. I hope you'll all pick that up. A number of things. Castle in that medieval warm period was on the coast of England, and they used to dump prisoners off the edge of that in the moat, and they'd float off to sea and they'd die. Today, that same castle is 1.5 miles from the coast. So the point here is that the warming that was apparent back in that day, 1200, was significantly warmer than what we have today. We went through, since that time, the Little Ice Age, thought about in 1750. The Thames River in Great Britain was freezing over, non-navigable, and so we have some global pictures that I think need to be identified a bit. One other point about CO2 is that, I want to give you an image. University of Michigan Stadium holds about 100,000 people. And if you took the concentration of CO2 in Earth's atmosphere and it occupied some seats in that stadium, they would occupy 40 seats. 4/100ths of 1% is the global concentration of CO2, 400 parts per million, which numbers mentioned here. And if you look at the contribution of human beings to the CO2 atmosphere, we're about 3.5% of that 4/100ths of 1%, or that would occupy one seat in that stadium. So for modeling to try to drive all the climate discussion from that one seat and assume that we are the primary drivers of temperature on the globe, I strongly disagree for a number of reasons, and that's just one. So, thank you.
Okay. Well, I came here at K-State in 1988, and I immediately got involved in a project looking at the effects of elevated CO2 on grasslands with Dr. Clinton Owensby. And at that time, the CO2 concentration was 350 parts per million. So in 25 years now, we've just crossed, backsliding around 400 parts per million. And it was interesting because the photographer mentioned that he was a climate skeptic at the beginning, and I was too. Because the models were very immature, the science was unknown. But I think things have changed quite a bit. The models have improved, science has improved, and there's more and more evidence that our climate is changing. Partly due to natural cycles, but I think it's pretty clear among 97% of the climate scientists that our climate is changing, and partly due to human activity. And so I guess that's one of the points. The other thing is, what I work on is I'm very interested in agriculture and how it's impacted by climate and improving Kansas agriculture. And so if the 3% are right, and I'm working on looking at carbon sequestration, improving the quality of soil, looking at better efficiencies, building efficiencies. 3% are right, then I think we've still done a good thing by improving Kansas drought tolerance, heat tolerance. And so, if that 3% is right, then we've still done a good thing. If the 97% are right and we don't do anything, then it's going to make it even harder to adapt and mitigate. And so I guess I look at it from a risk standpoint.
So this is the kind of scientist I wanted to be, and I never got to be. So I ended up working on computer models a lot, although I did quite a bit of field work in my earlier career. I think this was a movie made out of frustration at how to communicate this kind of thing. Communicating climate change is incredibly hard. We've already said 97% of scientists. What is that? So we have a real problem. Actually, every climate scientist, including the skeptics, will tell you that CO2 will warm the planet. There's no discussion about that. It was first figured out in 1859. We knew that humans had an impact by 1896. There's a long history to this. And so I think we need to keep that in mind, that this is not something that just happened last year. We have known this for a very long time, actually. The question is how to communicate it. If you were to ask me what's going to be the impact of climate change in the future, I've got to tell you, I don't know, because we don't know. We know that the planet is warming. We know it's going to warm more, pretty certain, because of the physics, not because of correlation, not because of something else. And we know that because of the physical relationships between CO2 and energy and radiation. So we use models to do that because it's the only tool we have. Well, models have problems, but we use all the same equations that the aircraft engineers use in Wichita. And how many of you would be afraid to get on a Boeing 787 on its maiden flight? Probably not very many of you, even though it had only been done in computer simulation. It's the same kind of physics. It doesn't change. So I think one of the things that we need to talk about is how to communicate the science, how to get this discussion going in such a way that we're not bickering about it, but rather that we see that it is a lot of gray shades. What we haven't seen since this movie, Greenland, for the first time and that we've observed, actually melted on the entire ice sheet at the top. That was last year. Last year we had the least amount of Arctic sea ice, that's ice that floats, we've ever observed. This year is going down towards that record too. So I think we still are seeing very rapid changes now. I think in addition to what we just saw, I think that the science is really, I won't say settled. There are always surprises. There are always other things that can happen. The real issue is not, does CO2 cause climate change? Yes, it does. We know it does. The question is, how will the Earth respond? And that's what we fight over as scientists, if you want to call it fight. Okay? We are discussing what will happen. How will the ocean respond? It's a big ocean. It moves a lot. How will the ice respond? The ice is actually a key here because it's something called the ice albedo feedback. When the ice starts to melt, instead of reflecting 80% of the energy, it absorbs 80% of the energy in the land that's exposed. And we know that that's starting to have an impact, and most of us think that things like we saw the drought last year, the heat wave in the West, the cold in Europe, are because the jet stream, which when we had a very strong energy gradient between the equator and the pole, 20 degrees or 40 degrees Celsius, is being reduced because we're warming the pole proportionally much more than the equator. And that changes the speed of the winds, which in turn changes the speed of the jet stream. And what does the stream do when it slows down? It starts to meander more. And what we're seeing is more meandering, and that's changing our climate in ways we hadn't really thought about even as climatologists 5 to 10 years ago. We thought about this gradual change, and now we're realizing it's not so gradual. You watch some of the new evidence from the ice core shows that there were some really, really fast, like 10-degree changes in the poles in literally a matter of years. We don't know if that's around the corner or not. Most of us won't talk about that because we're not really sure. And so I think there's also a question about how the scientists communicate, and we need to do a much better job.
Hi. This distinguished panel, I'm the token redneck on here. I serve as Kansas Farmers Union president. Kansas Farmers Union is one of the oldest general farm organizations in the state. And before I better read this right at the start so that I don't get lost at the end of our rambling. But we have written policy that's developed by our membership base. And right in our policy are written in regard to climate change is we support efforts to reduce emissions of heat-trapping gases and toxic pollutants. We support research for climate change adaptation. So this is part of what our written policy is. I personally and Kansas Farmers Union got involved in looking at climate change in the mid-2000s when we participated in a voluntary carbon sequestration program with the Chicago Climate Exchange. And that's when I got involved with Dr. Rice, and I started actually listening to him, and I went, holy crap. But that program actually went pretty well. I mean, for a voluntary program, we were the largest aggregator of carbon sequestration in the soil in the nation. Farmers Union was. We had millions of acres enrolled, and at its peak was distributing $8 million a year to producers that were doing carbon sequestration practices on their farms. my involvement in that, and I'm kind of an outspoken guy, and I ended up having the opportunity to speak before a congressional hearing on rising energy costs and climate change. So if you like seeing a really nervous redneck testifying before Congress, if you go to YouTube and type my name and somebody put that on there. It wasn't me, and it wasn't like I was an expert. These are the experts. I'm kind of a bullcrapper. But I do want to relay one last thing, and that's, I'm not a world traveler like Chuck is, but in 2010, I managed to get my butt off of the United States soil, and I went to Senegal, Africa, and worked with a village way back in there. And I was working with their farmers on millet production, but this village I was at was right out of National Geographic. I mean, no running water, no electricity, huts, and the chief of the village was about 900 people. The chief of the village was too important to be part of the group of farmers that were working with me. He was too dignified. And so one day we were out working with some farmers, and the interpreter came up to me and he says, the chief of the village would like to meet with you. Would you be willing to do that? Yeah. And so I follow him, and we go to his hut, and we go inside, and we sit down together with the chief of the village on his flea-bitten cot in his hut. And where he's sitting there looking dignified, and I'm sitting there wondering what's going on. And he started rambling away to the interpreter, and then the interpreter tells me, he says, the chief wants to know if I can tell him what's going on with the climate. He says the things that they could rely on and what they did, how they survived, is changing, and he wants to know what's going on and who's doing it. And that's when it really struck home to me that this is not, we might be contributing 26% of the carbon into the atmosphere in the world, but that's a world problem and not a United States problem only.
Okay, now we have some questions. So this one can go to anyone who would like to answer it, but someone asks, have studies like this that we saw in the film been done in the southern hemisphere?
Not the same way. And as Representative Hecky said, it is different in the southern hemisphere. It's a very different climate system. You have open ocean around it. You have a completely different circulation pattern. We also have the ozone hole issue, which actually changes the radiation that comes through the atmosphere there. I was just actually talking to someone recently. The area of sea ice actually is expanding in Antarctica. However, the sea ice also has gotten thinner. In some ways, a lot of scientists are looking at Greenland right now because it's easier to get to, it's more accessible, it's showing these nice changes through these glaciers, and we're learning a lot from it. But in Antarctica, we've seen actually even much bigger changes. There have been huge chunks that have fallen off there that made what you saw in the movie look like nothing. On the other hand, there has, in some places, been some thickening and others thinning, but that happens when the ice moves. We do know that several glaciers have really sped up over there too now, and particularly there's something called the West Antarctic Ice Sheet. There's a mountain ridge that runs down the middle. That ice sheet is not anchored on the ground. Underneath, the ground level is below sea level, deep, like several hundreds of meters. And so the problem there is that if water gets in, the whole thing can float, and we really don't know. In fact, from a science perspective, that's a much scarier ice sheet. And it's about less than a quarter of the entire Antarctic. So to us, that's a much more worrisome thing, and we've seen a lot of change there, particularly the ice. We now have ice streams that run through these, actually what we think of as big ice masses. And our complete understanding of this has changed in the last 10 years, in part because these places are so remote and it's so hard to get visible evidence.
Did you want to say something else?
I'd be happy to comment. The average annual temperature in Antarctica is minus 42 degrees Fahrenheit. So it is not going to melt. It never has melted. and we have no fear of losing the ice. As Dr. Fetterman just verified, the sea ice extent is at record levels. Maybe it's thinner, and maybe the calving is increasing, and that's just fine. That's what glaciers do. They calve all the time. So I have no concern whatsoever about what is going on in Antarctica with the southern hemisphere differentiation with respect to the northern hemisphere. We have a global system, and we need to look at the entire globe at all times and simultaneously. So you have glaciers in Switzerland, which have been receding ever since the end of the Little Ice Age. The Little Ice Age did occur. It ended at about 1750. There's a complete record associated with that. It's not an imaginary event. And so we've just got to be a lot more sensitive to the real data that is out there. And I want to speak a bit more about temperature data. And I think we can get verification of this right here at this table. The way that temperature is measured and the global temperature you hear about is a sum of global stations around the world. And a couple decades ago, there was a decision made by some people at a round table to discontinue temperature measurements in the higher latitudes and the higher altitudes of Russia and Canada, for example. Material decreases in temperature stations in those very cool regions. And so the temperature record that we now have is, of course, sensitive to these deletions. And so your global increase in temperature is in part, I think, manufactured in terms of what's really going on in global temperature. We really have a flattening of global temperature, if not a slight decrease actually happening. So, thank you.
This next question, I think before we get to the question, because of the way it's worded, can one of you explain what a positive feedback loop is?
So positive feedback is like the feedback when you get the microphone. So the thing is that you have a state of equilibrium, let's say, and you move away from it, so you warm up a little bit, and then something happens, and a negative feedback will bring you back towards the mean. Positive feedback will then bring you away, and it will keep going. So the thing I was explaining about the ice is a positive feedback. Melt a little bit, makes it warmer, melts it more, makes it warmer, melts it more, makes it warmer. How long do you go? Until the ice is gone. And that's when it stops, because there's nothing to stop it otherwise. In a negative feedback, you go back towards the mean. So something happens. For example, you might increase cloud levels, right? So when you increase clouds, that means less solar radiation is. So let's say it gets warmer, you evaporate more water, you create more clouds, you reduce the amount of sunlight. That means it starts to cool off. You reduce the number of clouds again, you're going back to the mean. So a positive feedback is a runaway system.
So here's the question, which is really more of a statement, but I'll read it as it's written. Several positive feedback loops are increasing greenhouse gases. CO2 and methane both stay in the atmosphere 100 or 20 years respectively. Thus, we should be discussing how to adapt to climate change. It is changing now and in the future, even if the greenhouse gases are all stopped today, which is totally unrealistic to reality. So, do you think that we should move our conversation away from, this is, I guess it's the question, should we begin to talk about how we will adapt to that rather than what it's actually doing?
Sure. Well, it's pretty clear the conversation changed about in the last 10 years, at least for the United States, in particular for agriculture, because it's all about mitigation, how we can reduce greenhouse gases. But even if we did, like the statement made, even if we stop, we've increased about 0.6, 0.7 degrees centigrade now. Even if we stopped, it would warm another 0.7 degrees. That has significant implications on agriculture, and so there's already increased investment in how to adapt to climate change as well as mitigate. So that's, and again, kind of like the things I talked about, heat tolerance, drought tolerance. We're going to have to figure out those systems or cropping systems that are more resilient.
They alluded to it a little bit in the film, but what's really starting to glaringly show here in the United States is in the insurance industry. I serve on some boards, and our nearest neighbor to the south, Oklahoma, is really the worst example in the nation right now for natural disasters that are affecting insurance rates and causing catastrophic problems within the insurance industry. And that's not, I'm no expert on the East Coast, but I do know what's going on to the south, and we're not that far off either, so the economics is in there.
I'll just repeat real quick. Don made an important point, because back in the 90s, when there was a lot more questions about climate change, some of the meetings I went to, it was really interesting, because a lot of the insurance agencies were there, and I was trying to think, why are insurance agencies interested in climate change? Well, it was because of risk and changing their insurance agent or infrastructure. The other interesting was the Department of Defense was highly involved and interested in climate change, so they could figure out where the hot spots, the stressors were going to be, to figure out where conflict, predict where conflict was going to be. So even then, defense was kind of following climate change science to better predict where their needs were in the future.
Thank you, Carol. I want to have you look at a couple of slides that are in my package, but I want to spend a moment here discussing both of them. This is a slide that you can see from where you're seated. It shows a record since 1950 to today of the number of strong to violent EF5 tornadoes. This is NOAA data. Now, do you see an upward trend in the last 2 or 3 decades? Do you see you do? Well, I'm sorry, but I don't see an upward trend of any magnitude in this data. Maybe I'm just not reading it correctly. The last 2 bars are the last 2 years, but the last 3 or 4 decades are, if anything, a downward or a flat trend. There's no support for the suggestion that we have more violent weather because of CO2 and global warming. I'm sorry, it just does not exist. The final point I want to make here in this brief moment is we've been talking about CO2 and temperature. This is an actual data record from 1940 to 1970. It's a 30-year period. The upper graph, the upper part of the graph is CO2 concentration. It is increasing just about the same rate that it's increasing today. The lower portion of the graph is global temperature during the same period. I think you can see from where you're seated that the global temperature trend during that 30-year period, while CO2 was dramatically increasing, was materially going downward. And that's not the first time that's happened. We're having it happen today. The temperatures are going down. The global temperatures have been flat, if not downward, for the last 15 years. So I just submit to you that we've got to be very careful, and we need to honor the actual data, not homogenized data, not adulterated data, but actual data. Thank you.
Go ahead.
Actually, I'll skip. Go ahead.
The next question, this may actually play into that. Please explain and discuss the strengths and limitations of climate models.
Wow. Do we have all day?
Oh, you have 2 minutes.
For you to get a real grasp of this, it would literally take all day. There's just no way around it. So I can't answer that question in 2 minutes, neither can anybody here. You need to read. And I would recommend you start with the IPCC report or the U.S. National Assessment Report about how these things work. Models are interesting because they're a mixture of things. There are things we understand quite well, like the physics of radiation. We understand how components of the atmosphere, just like if I put 1 drop of cyanide in this room, you'd all be dead. It's a tiny fraction of the air. CO2 is a tiny fraction of the air, but it plays a very big role in radiation because nitrogen, which is most of the air, does nothing. So we can't talk about a Michigan stadium of CO2. It doesn't matter because it has an impact. And it is important. There are other concerns because when we talk about climate system, like was said earlier, it is a global system, right? So it's not just CO2 causing the temperature to go up. The oceans are moving around, they're changing, currents change. We know there are natural cycles, as people like to point out, okay? There are natural cycles in the Earth's orbit that actually cause the ice ages. There are cycles in the ocean that cause 50-year warm and cool periods, okay? But if you look at that graph, and you don't look at 30 years, but you look at least as long as we've got, and then look back all the way from other data like the ice core, you can see that actually there's an ongoing long-term trend, but it's kind of a stepping case thing. And instead of doing nice oscillations like this every 50 years, we're doing 50 years like this, right? So looking at a 10-year record isn't really very meaningful because you're not incorporating in what's going on in the entire system. So I would point back to what Representative Hedke said. We have to look at the entire system and understand it. There are a lot of papers out there. John?
We have two other questions up here. One is for Jim Daylog, and one is for Al Gore, and since neither of them are in the room, I'm going to...
I want to comment on the modeling question. And we have two gentlemen here who have participated in the IPCC effort, and I know other people who have done that and been involved with it, personal friends of mine. I'm going to show you another graph. This is going to tell you about modeling accuracy. And this graph right here goes from 1993, this is a small time frame, but 1993 to 2100 projection. And the red outlined area is the projected sea level rise according to IPCC modeling. That's this trend here. Okay, upper trend, IPCC modeling. The actual sea level rise that has been projected is a small line on the very bottom of that graph. You may not be able to see that from where you're at, but trust me, the trend is consistent over many centuries. It's not materially changing. It's about 6 inches per year, maybe 7. And so the modeling that the IPCC did was outrageously wrong. And I'm sorry, that's just the way it is. And so we've got to be really careful with the modeling. I have two other graphs that I want to share with you. IPCC modeling did get this one kind of right. It's a temperature model, and the black line shows actual results. This is warming over the Arctic. Okay? The next one is warming over Antarctic region. I'll be just about done here. And the blue line on the very bottom are actual results compared to the other indications of the models. Okay? So the modeling has serious deficiencies with respect to CO2 introduction and its assumptions. Very serious deficiencies.
Okay, let's do a science question here, I think. Have there been any studies to track the amount of carbon sludge, like with what was shown in the film, in correlation to ground temperature? And also any study to track any correlation with the amount of sludge to the speed of glacier melt? That was that, I can't remember what it was called.
People have, yeah, actually people have looked at what we call a black carbon deposition, usually, like we refer to it. The problem with it is that it's black, right? So when it settles on the ice, it changes the color a little bit, and all those black absorbs heat, and the white reflects it. So that's why you get those puddles, actually. People have looked at it, but I don't think it doesn't really change the temperature that much, because you're sitting on ice, right? And it's at freezing temperatures no matter what you do. So even though the black particles might sink into the ice and help it melt faster, the temperature doesn't change that much on top of it until the ice is gone. So again, it's a very complex interaction of things, and almost none of the things we've talked about here are as simple as they appear to be. Nothing is black and white. There's always these complexities that we have to deal with, and this is what makes it so hard to communicate about this, because it isn't just something like, the IPCC's maximum estimate of sea level rise is less than a meter, and that 6 inches a year, that's 600 inches. That's way more than a meter. I don't know how many it is, but that's not the record that I know of. So, I think 6 inches per year, you said.
6 inches per 100 years. I apologize. 6 inches per 100 years.
Well, the other issue we need to think about is this is not a linear system. Nothing is linear. I don't know if you've ever looked at a population growth curve, an emissions growth curve, a resource consumption growth curve, a insurance growth curve. They're all exponential. How far can it go until you hit some limit? And I mean, I think that's the way to sort of think about this system.
Here, remind me of that question, please.
Carbon seed, black carbon.
It was, yeah, about the carbon seed.
Thank you. I want to make a distinction between carbon and CO2. Carbon is black. Carbon is an element. CO2 is a compound. It's colorless, odorless, and tasteless. And it's a harmless gas, certainly at the concentrations that we experience today, and for all intents and purposes for many hundreds of years. We have submarines where our sailors live in an environment where the CO2 concentration is 8,000 parts per million. We're talking about 400 here in the current climate. So there's a factor of 40 times, which is very safe according to the government. I'm sure our sailors would be living in that environment. And so we've made this assumption that CO2 is somehow a pollutant. And that's what the president's recent statements indicate. Carbon pollution. It's related to CO2. It's not related to carbon. We're trying to attack CO2. And so I'm sorry here, but we need to get an understanding of the chemistry. And we're not changing the chemistry of the planet, such as what Dr. Balog indicated. Nothing of the sort is occurring, at least in terms of human activity. The volcanoes are spewing out all sorts of CO2 all the time, and they'll continue to do that, whether we like it or not. They're the largest contribution of CO2 in the global system, aside from the oceans. And the oceans are warming, and they release CO2 when they warm in large amounts. So the sun and the oceans dominate the climate of the Earth, dominate it. And so I just hope that you can appreciate that the suggestion of CO2 being a pollutant is a fallacious argument. There's no basis whatsoever about that suggestion. None. Thank you.
Let's move on to another question. For Kansas and the High Plains, the 98th meridian, what are the climatic conditions likely to be? Windfall, rainfall, humidity, growing season within the next decade? Is that crystal ball there that's on?
Okay, there is no crystal ball. I'm sorry. We can't do it. We can't. It's too small an area. Okay? When we have a global climate model, we use physics. We actually use other statistical relationships between variables and all kinds of things are mixed in there. It's a very complex system. But the problem is we can't simulate everything. We can't simulate we're just starting to learn how to simulate how much you're irrigating. We've done some model runs at KU where we're looking at what irrigation might be doing to this particular region and the whole Midwest. And what we're finding is we're cooling the surface perhaps, because just like sweating, irrigation cools the surface. Okay? But what we're doing is pumping a lot of water into the air in that very process. Where does that water go? Well, it goes with the low-level jet up to Minnesota,